Class is now starting. All attendees are in listen-only mode.
Good morning. We'll get started here in about another minute. So just hang out for about another minute. We'll be right back. All right. Good morning, everybody. Thank you for attending the Trade Alley webinar today on energy recovery ventilators. Okay. We'll go over some program reminders, rebates, and then we'll hand it off to Ryan from TEC. Trade Ally landing page, as we discuss every month, please visit tradeallycenter.com. You can access the available resources like program documents, upcoming events and webinars, past presentations, webinars, videos around there, case studies, program updates, and more. Future webinars. Next month we'll have be talking about steam boiler blowdown heat recovery. That'll be with Tony Rinaldo from Boiler Source. And then we are looking for any suggestions for webinar trainings for next year. After November, we take December off because it falls on the holiday. But yeah, anybody's got any ideas, please feel free to contact me with any training ideas. Like I said, any recommendations, please get a hold of me. Get a hold of me at gmaxim@franklinenergy.com, or there's my cell phone, or just you can go on tradeallycenteralso.com and send out a message. Now I will hand it off to Ryan, if I can figure this out. Let's see. All right, I just handed it off. Ryan, you there?
Yep. Let me show my screen.
Yep, looks good. I can see it.
Awesome. All right. Well, thank you for having me back. I love doing these. Sorry that we didn't do it on a Wednesday like normal. Mixed it up a little bit this time, some scheduling changes, but here we are. So energy recovery ventilation is the topic. There are the opportunities to double dip your rebates in this regard. You can get a gas utility rebate, obviously Peoples and North Shores we're talking about today, and you can get an electric rebate, probably ComEd if you're overlapping with Peoples and North Shore, all on the exact same project with the exact same widget, because there's electrical savings and gas savings for nearly every ERV. So on the gas savings side of the equation, for Peoples Gas and North Shore Gas, this is the rebate amount. It is 75 cents per CFM input, and we'll go through what the CFM means. But just to make things fairly clean, if I had 1,000 CFM ERV, that'd be a $750 rebate, right? If I had a 10,000 CFM ERV, it'd be a $7,500 rebate, and so on, kind of thing. There are some rules on here, but the vast majority of ERV products will comply with this. Operating 2,000 hours a year, not hard considering there's over 8,000 hours in a year. So this is pretty common that would work. It's got to be related to gas-fired equipment, obviously, because it's a gas rebate, so it has to save gas. And then you have to be bringing back at least 65-degree air on the exhaust side, which is not hard to do. Any given space, any office, school, retail, or anything like that you do is going to have more than 65-degree return air going back to the air handler. So there's a few rules in that regard. If you're outside of those ranges, you can always do a custom one as well. But if you can stick with the standard rebate, which is the one we're showing on the screen, things are significantly more simplified. This particular rebate is for the sensible recovery. You can do latent on the custom side, but you're not going to get that much more on the gas side of the equation by adding in latent energy to this discussion. So it may or may not be worth the paperwork. If it's a little ERV, not worth the custom paperwork. If it's a giant project, okay, then it's worth some custom paperwork. And then for the double dipping side of the equation, on the ComEd side, which most North Shore and People's customers have ComEd as well for the electric, you can get 20 cents per CFM if you do a wheel style, and 10 cents if you do a plate style ERV. We'll talk about what both of those things mean if you're not already familiar. So the ERV's job in life, he's bringing fresh air in. Say he, it's not a human. The ERV is bringing fresh air in, and there's numerous reasons why we need fresh air, and there's codes that require fresh air, so we don't need to really beat that horse to death. You have to do it. You have to bring the outside air in. So if you're going to bring outside air in anyway, somewhere else in the building, you're going to have to exhaust air. Otherwise, the pressure is going to be all jacked up in the building. So why not save the energy, the heating and cooling energy from the exhaust air, and use it to precondition the incoming air? I'm not saying mix the air. The two air streams will stay separate, as you'll see. But why not have the heat from the air that's leaving the building be used to warm up the air that's coming in from the building on a cold, 10-degree day or something like that? So we got to bring the fresh air in the building anyway. We also should distinguish that there are fresh air requirements for buildings, and then there are combustion requirements for outside air for buildings. And those are two separate, unrelated things. So in the boiler room for the same building, you'll need combustion air coming into that boiler room just to be consumed by the combustion process of the boiler or furnace or other things, as you can see on the list. And that air is going to go right back out. It has nothing really to directly do with the pressurization of the building. What we're talking about now is not that combustion air. We're talking about fresh air coming into the building, unrelated and in addition to this combustion air. And we're not going to bring it into the boiler room. We're going to bring it in through the air handling system. There are also sources of exhaust in the building that you have to do by code for certain things, like bathrooms. Everyone's probably aware there's an exhaust fan in every commercial bathroom. And there's other spaces too. And that air, we can sometimes recover the energy of that air and use it on the ERV. So the combustion air is never going through the ERV, but exhaust air in the building might. What kind of exhaust air might? Bathrooms might. Locker rooms might. Kitchens, we're not going to use that exhaust air. It's going to be sticky, gooey, caustic, all that stuff. We're not going to use it from some kind of, weird chemical process, things like that. But normal building exhaust stuff, we absolutely will. So how much outside air does your building need to bring in? There are tables we can look at that show the ventilation rates over time. And lots of different places have different ventilation rates. Currently, other than the city of Chicago and the state of Wisconsin, pretty much everyone else is using their National Mechanical Code or ASHRAE 62.1, which have the same tables as each other. So in all those places, so all the suburbs, for example, this is the table that you'd be using. Chicago's a little bit of a different beast. This is just page one of like 4 different tables. And if we zoom this up and just look at a specific scenario, say an office building, because that's my favorite one to look at, and it's very common, I need 5 CFM for every person that's going to be in this given space. Whoa, what happened to my arrow there? Pretty fancy. And I need 0.06 CFM per square foot, and I would add those two things together. So if I had 100 people in a space, I would need 500 for them. And then if I had 10,000 square feet, I would need 600 for the building. I would add those together, and this space would need 1,100 CFM of outside air to be brought into the building anytime the building is occupied. And that would be for pretty much every suburb and everywhere in the country for the most part, except for, like I said, the state of Wisconsin and Chicago. Chicago's a little weirder. Chicago requires a certain supply air CFM into the spaces, which is odd because normally supply air is dictated by your load calc, not by code. And then a third of that supply air has to come from the outside. So as a result, generally for most projects, Chicago has the highest ventilation rates of anywhere in the country. Wisconsin, in contrast, has the lowest ventilation rates in the country. The higher the ventilation rate, the more sense it makes to do something like an ERV where I can recover energy, because I got to bring a lot of outside air in. I want to do that very cost effectively. So ERVs have a significantly better payback in the city of Chicago than they do anywhere else in the country. Not that it's bad in the suburbs and the rest of the country. It's just really good in Chicago because there's a lot of outside air requirements. ERV, if you're not familiar with that term, energy recovery ventilator. Sometimes it also stands for enthalpy recovery ventilator. And that's when we decide to divide the ERV topic into 2 different things. We'll have enthalpy recovery and we'll have heat recovery, HRV. HRV means I'm only going to do temperature stuff, just sensible energy. Enthalpy recovery ventilator means I'm doing sensible and latent. temperature and moisture recovery. And then energy recovery ventilator is just a generic acronym, because we got to have a lot of acronyms in this industry to kind of encompass all of them. Whenever we're talking about one of these type of projects, or potentially one of these projects, the first question that must always be asked is how much outside air are you required to bring in? If you don't need a lot of outside air, this isn't very exciting. You can do an ERV on a residential home, but if you only need 60 CFM coming into a house, it's not super exciting. The payback is going to be like 28 years. No knock on residential ERVs. We do tons of them, and there's lots of reasons you might want one, but payback is not one of those reasons. Commercially, however, if all of a sudden I have 2,000, 3,000, 10,000 CFM of outside air, now these paybacks get really quick. Really quick meaning months. The thing pays itself in months in some cases. The larger the system, the more outside air you have coming through the system, and the more exhaust air going with that, the faster you'll be able to pay down the technology cost. This is not new technology, by the way. We've had this for decades and decades. At least at our office, we've been using it a lot for the past 20 years. And prior to that, we didn't use it much, but it was available. If I want to take energy from the exhaust air and save the energy and transfer it to the ventilation air coming in, I'd like those two air streams to be near each other. I don't want to have a fresh air intake on this rooftop over here on this side of the building, and then 300 yards away across the other side of the manufacturing facility have this exhaust system. That's going to be really tough to do. Not impossible, but not really easy. I like these things to be as close as possible, and then it becomes significantly easier to do. Fortunately, for many projects, like say an office building, the HVAC equipment serving a certain area of the office probably also has exhaust fans near that area of the office, because that area of the office also has its own bathrooms and its own pressurization exhaust and all that stuff. So you can group this stuff together usually pretty well. So to give you a couple examples so you can understand the magnitude of what we're talking about here, there's a summer on the left, winter on the right. I guess we'll do winter because it's probably a little bit easier to understand. So there's 4 air streams on an ERV. This one happens to be a wheel style. I'll show you other ones in a little bit, and we'll explain how a wheel works too. There's 4 air streams. There's the outside air coming in, the code required ventilation air, or it could be even more than code air, but at least the code required ventilation air. There's exhaust air leaving the building. So this is air you were going to get rid of anyway for pressurization reasons, because it's a bathroom or something like that. So exhaust air is leaving, and I want to take that dude's energy and I want to transfer it through this heat exchanger, a wheel in this case, to the outside air coming in. The dirty air molecules are still going to leave. The clean air molecules are going to come in, but the heat from the one is going to go to the other. And I overlapped on top of so I can't read. So in this case, I have 72 degree air, 54 wet bulb, so relatively warm, middle humidity air that I was about to throw away and just get rid of it and chuck it away. At the same exact time, I am bringing in 6 degree wet bulb air, which is cool, cold even, dry air that's going to make my space cooler and drier. When I take the energy out of that return air and transfer it to that outside air coming in, that 7 degrees in this example warmed up to 53 degrees. And I added moisture, because this is an enthalpy recovery scenario, to go from 6 wet bulb to 40 wet bulb. So now on a 7 degree dry day, the occupants of that space will be receiving 53 degree cool air that's medium humidity. Now obviously there's still going to be an air handler with a hot water coil or a rooftop with a gas furnace or something like that, heating it up the rest of the way. But that probably gives you an idea there. On the cooling side of the equation on the left, it's very similar, but in this case I have a nasty day. It's 95 degrees, 78 wet bulb, so it's like basically the hottest, most humid, gross day we would typically get on any given summer in Chicago area. And I'm about to throw away 75, which is reasonably cooled air, 63 wet bulb, which is reasonably dehumidified air. I'm about to throw it out. I'm just going to let it go out the exhaust system. So instead, what we do is we take the temperature and the humidity from the outside air and we transfer it to the exhaust air going out, raising its temperature and humidity, thereby cooling down the temperature and humidity of the air going into the space. We dropped it from 95 down to 81. We've dehumidified it from 78 down to 68. 81 and 68 is not going to be awesome enough to cool your building, but it's a really good starting point. Pretty much every evaporator coil for every commercial or residential system is designed with 80-67 as the expected entering conditions to that evaporator coil. At least that's where the manufacturer has selected it and rated it with AHRI. Whether you have that or not is another debate. But in this case, I'm 8168 instead of 8067. It's like I almost don't have any outside air from a thermodynamic standpoint. I pretty much pre-treated it, so it's pretty much return air in terms of its temperature and humidity. So it's pretty fantastic if you think about it. Like I said, you can't really do it on really tiny stuff very well, but on medium and larger projects or medium and larger systems, 10 tons and up kind of thing, you can recover quite a bit of both summertime and wintertime energy. And more importantly, not that I'm against saving energy or anything, obviously I'm in favor of that. More importantly, you can provide better comfort conditions to the occupants, and you're doing it with less energy. So it's like a double win kind of thing. So benefits, as just mentioned, better temperature control, better humidity control, which is fantastic. You can literally buy a smaller HVAC system. If I'm going to pre-treat the outside air coming in and make it cooler or warmer than it would otherwise be during that season, I don't need as big of a compressor. I don't need as big of a gas-fired heat exchanger. I don't need as big of anything. Well, I still need the same size fan, but I don't need anything else to be quite that big. So you can reduce the size of the equipment, which does save some cost on the project. Now you're buying more stuff with the ERV, and we'll talk a little bit about how that trades off. But you might buy a smaller HVAC system, smaller boiler, smaller chillers, smaller rooftop, smaller coil, smaller whatever, and trade that money off for buying an ERV instead. Paybacks are usually really good on larger systems. What I mean by larger systems, kind of the magic cutoff point seems to be around 1,500 CFM of outside air. If you need that quantity of outside air, you're probably going to have some pretty good paybacks. So in this case, 1,500 CFM of outside air is going to reduce the size of the cooling I need on this application. And I probably should clarify too, this entire chart is kind of just a cheat sheet chart that I have not updated in a long time. In fact, someone else made it, so I stole it and I didn't update it. But it just kind of gets us in the ballpark. But this is assuming you're replacing a rooftop in this application. If you're doing other kinds of equipment or it's not a replacement project, then it'd be a different cheat sheet, right? This is assuming you're taking off a bad rooftop, you're going to chuck it, you're going to buy a new rooftop, and instead of buying a new same size rooftop, you're going to buy a smaller one combined with an ERV. When I do that in this example with 1,500 CFM of outside air, I'm going to be shopping for a rooftop that is 4 tons smaller. So if previously I needed a 20-ton unit, I am now in the market for a 16-ton rooftop unit, right? And I'm looking for one that's 120,000 BTUs of heating smaller, right? So whatever I thought I needed before, or the old one was, and I'm going to go down at least that much and get a smaller one. This particular one is designed to get 8067 off of the ERV. That's chosen that way on purpose for the reasons I said earlier. And then in the winter time, I'm going to be looking to try to get 50 degrees off the wheel. We're usually trying to get to this 8067 because it's kind of a nice point because it means the HVAC equipment from a cooling standpoint doesn't have to be special. It can be regular rooftops, regular air handlers, regular things that are not sexy. Whereas if I have a lot of outside air and I don't have an ERV and I'm not starting with 8067, I have a much wider swing, so I'm going to need different kinds of capacity control to do that. The temperature coming off of in this case, the wheel into the space is 50 degrees, and this is on a negative 10 degree day. So we're getting a 60 degree heat rise. This whole chart was based on 95 degrees cooling and negative 10 on a heating day. So like the worst days that you're probably going to encounter on any given year. But yeah, 60 degree heat rise for the price in this case of pushing air through a heat exchanger. That's it. It's a pretty good deal. This one happened to be a 1.6 year payback, saving $1,400. It might seem a little bit weird, but the reason why the payback is 1.6 instead of like 4 or 5 years is because we're getting a credit for buying a smaller rooftop than we were going to buy. Instead of buying a 20 ton, we're buying a 16 ton, or most people don't have a 16 ton, so you're going to get a 17 and a half or something like that. But I'm buying a 17 and a half ton instead of a 20 ton. I'm saving X amount of thousands of dollars there and applying that money over to pay down the ERV a little bit quicker. And then you throw in some utility rebates, and then obviously the energy savings. And in this particular case, I'm at a 1.6 year payback. Show you one more in here just to give you a more extreme example. This is 12,000 CFM. So this is a big ass air handler in this case, or rooftop on this chart. I need to find a rooftop that is 31 tons smaller than what I was otherwise trying to find. So if I was looking for a 60-ton rooftop for my project, I'm now in the market for a 29-ton rooftop, assuming I can get one that has the fan capacity that I need. This one's really attractive in this particular example. That's why I picked it. It's going to be almost 1 million BTUs less heating for that rooftop, and it's a 0.1 year payback. It's basically a 1 month payback. The whole thing pays itself in 1 month. I picked that one because it was the best one on the chart, obviously, to kind of make it look exciting. But the reason that happens is, for most of you, you probably know, once you get out of the large rooftop sizes and you can get down under 30-ton sizes, for example, you are more in commodity land of rooftops, package rooftops. Every manufacturer has one that's below 30 tons, right? Every manufacturer has 2 or 3 tiers of options below 30 tons. But when you're above 30 tons, all of a sudden you only got like 6 manufacturers and they only make one model. Maybe there's 2 and it overlaps a little bit. But you have less choices and there's a lot more customization, so the price is higher. You get the price down and you're buying Model T Fords. Right? That's why this one was such a good payback scenario. Glenn, if anybody asks any questions, holler. I'm trying to check it. I don't see anything right now. But if somebody types something in and you notice it, just scream at me.
Yeah, I will do. I'm watching it. Thanks.
Sweet. And if you guys have questions, please ask them, because mainly it's more fun for me if you ask questions. And the whole entire event is about me and my enjoyment. So if you could just ask me questions, that'd be great. So the kinds of ERVs that we use in the HVAC industry, the example I showed you a minute ago was a wheel, so a rotary heat exchanger. There's also fixed plate heat exchangers. Those are very common as well. And those two probably make up 95% of the ERVs that you're going to see. And they come in different types of flavors within themselves. There's also heat pipes and runaround coils, which are not, generally speaking, compliant with the energy code. Not because they don't save energy, but they don't save any latent energy. So on the sensible side, they would comply with the code, but the latent, the moisture side, they can't do anything at all. 0 latent energy savings. So HRVs are not something that the energy code would require. They don't prohibit it. You can certainly do one. But if you're in a project where the energy code kicks in and says, hey, because of this situation of your project, you have to put an ERV in, it has to be an enthalpy one. It cannot be a sensible one. And we'll go through that on the code perspective. The 2 code things that drive everything, as mentioned earlier, ASHRAE 62, which is also the International Mechanical Code, or same tables as the International Mechanical Code. That's requiring people to bring fresh air in. ASHRAE 90.1 is our energy standard. It feeds into the energy conservation codes, requiring people not to waste a bunch of energy while they bring the outside air in. And these things are not, they feel like they're going opposite direction from each other. Oh, bring a crap load of outside air in, but don't spend any energy to do that. So an ERV is the way that gap gets bridged, if you will. I just realized I probably should have I should have tweaked this one. This shows the 2012 code number, which is 50%. When we switch over to the new code here, it's actually 60% enthalpy. It's not a big deal, and probably why I forgot to change it on here, because there's not very many ERVs that are between 50 and 60% enthalpy recovery. Almost all of them already do 60%, so it's pretty easy. You just can't use an HRV if you're trying to comply with any energy codes. It's got to be an ERV. We are climate zone 5A. If you didn't know that, there's this magical line that divides the country into the moist and the dry area. We are in the humid moist area, and then vertically we are in the green area, which means we are the climate zone 5 for our temperature-based stuff. So we are 5A over here. What that means, when I go look at all the various tables, I just look at the ones that say 5A. I don't care about any of the other rows unless I'm doing a project out of state. So with our current energy code, and by the way, we are on IECC 2018 for X amount of minutes more. The state keeps teasing us and saying they're going to change it for like the past year and a half. City of Chicago went ahead and pulled the trigger, and they changed it in January to the 2021 version. But the rest of the state is just kind of like right on the fringe of changing here. But for this example, it's going to be the same difference. Other stuff in the code changes a lot, not this particular topic. If you operate your system less than 8,000 hours a year, meaning you're not going 24/7, a full year is 8,760 hours a year. So if you're a full-time operation 24/7, you're in the bottom table. But if you're not a 24/7 operation, you're in the top table. And if you had a project where you were bringing in 20% outside air, if it was 16,000 CFM on the fan or larger, you'd have to put an ERV on. that's not a very common system. That's a pretty big system, 16,000 CFM. But if you have a larger and larger percentage of outside air, then the rules beef up, right? So if I had something that was going to bring in 40% outside air, now all of a sudden, if it's a 4,500 CFM system supply fan, I have to do it. This is not the cleanest way they could have made the table. They should have made the table based on outside air CFM, but I think they did it based on the supply air CFM because it's easier to police, because anyone can just take the tonnage and multiply by 400 and figure that out. So maybe that's why they did it. But essentially what they're trying to do is use the percent of outside air and the supply CFM to inadvertently tell you what outside air CFM and ERV would make sense at. If you're going to occupy 24/7, you pretty much just have to do an ERV. I mean, you don't have to, but you pretty much have to. You're in this bottom row over here, and you can see the numbers are all tiny. They're like tens or hundreds of CFM. So if you have any outside air on a building that's 24/7, just plan on putting an ERV in. What does that mean? That means if you're doing a Walgreens, a CVS, a BP gas station, or anything like that that just never closes, you're going to have to do an ERV. You just will. Kind of the way it goes. There are some exceptions on when you don't have to do an ERV, at least right now in the 2018 code. And that is, like I said, it's got to be 50% recovery. When you change the 2021 code, it'll have to be 60% recovery, which is what I mentioned earlier. So the city of Chicago is 60% now. The suburbs are 50% now, just the kind of the tier of ERV you need. And then for the city of Chicago and eventually the state of Wisconsin, the vast majority of these exceptions will go away. The ones that come up now a lot that people utilize are exception number 9. You don't operate more than 20 hours a week, you don't have to do this. You don't have a lot of outside air, right? So if you're a church and you're only going to operate this air handler on Sunday morning and Wednesday night, you don't have to do an ERV, right? But other places would, right? The other one that gets utilized a lot is number 8, right? What this one basically says is if you got a bunch of little tiny exhaust fans, think of like an apartment building, for example, where everybody's got their own exhaust duct, you don't have to do this because it's really hard to group all these exhaust ducts together and run them through an ERV. And putting one little baby ERV on every single apartment would be not cost effective. However, that number 8 exception does go away in the 2021. And for apartment buildings that you're building now or gut rehabbing, you will have to put ERVs in those. So if you're in the city of Chicago now and the suburbs in X amount of months, I don't know what X means at the moment, you will have to do this on apartments as well. But there's a lot of existing buildings too, and that's where the rebates really help out. Maybe not an apartment because they have individual exhaust fans, but on offices and schools and labs and hospitals, there are tons of places that the outside duct and the intake duct are 20 feet apart. You can easily start recovering energy from one to the other. So as mentioned, Chicago did pull the trigger on the new code, and it does remove the exemption for those apartments, like we previously had just discussed a minute ago. And it bumps it up to 60% recovery instead of 50% recovery. Applications that this makes the most sense, places that have a decent amount of outside air. If you don't need a lot of outside air, let's say you're doing one of those little cell tower buildings, right? They got the building sitting next to the bottom of the cell tower. It's, a 30 by 20 box and there's no people in there. You don't need any fresh air. So why would you have an ERV? If you don't need a bunch of fresh air, an ERV doesn't do anything for you at all. It only helps you recover energy from air you were going to exhaust anyway and bring that energy into the outside air you were going to bring in anyway. So places that have a lot of outside air requirements are the best applications. Gyms, fitness centers, show theaters, schools, daycares, these places all have a lot of outside air, hospitals, nursing homes, so they make the most sense to do an ERV. We do have restaurants on the list. Just be careful. That's like the dining room side of the restaurant, not the kitchen side. We don't want all the grease from the kitchen hood trying to make its way through an ERV. So just kind of keep that in mind. Same thing with schools. Like if there's like certain like lab areas and you got like a bunch of wood dust going out the exhaust fan, we don't want that on an ERV either. But the rest of the school, yeah. You probably have seen this chart or a chart similar to this in the past. Basically what this says is when it gets really humid, bad stuff happens. When it gets really dry in a building, different bad stuff happens. Keep stuff between 30 and 60% and less bad stuff happens. Sounds really easy, but it's actually fairly challenging to keep the humidity in a building between 30 and 60%. Or in this case, it's showing 40 to 60%, which is even tighter. There are a sick amount of buildings that are above 60% humidity on an extremely regular basis. And there's lots of reasons for that. And if you've been on any other classes or webinars with me, you probably know that the number one thing I complain about is oversized equipment. Oversized cooling equipment does a really bad job dehumidifying. Even when it's correctly sized, if it doesn't have good staging ability and it has a lot of outside air, it's also a sloppy mess of humidity. What do I mean by that? We've got two columns here we'll look at. One, this piece of equipment is, it's the same piece of equipment in both columns, but it's running on a system that is fully occupied, meaning everybody showed up, meaning they're all giving off heat and they're all sweating and putting moisture in the air and breathing and putting all that stuff, right? And it's a hot, humid day out. Like, it's all those things, right? The day it was designed for, essentially, a design day. And in this case, this air handler is doing 15,000 CFM. I got a dew point of 53 degrees off the coil, which means it's plenty dry to absorb a bunch of moisture when it goes into that space. And my result is a 75-degree room at 48% humidity, and everything's great. By the way, it says 75 on here because if you didn't know, at least for the past 11 years, statewide, both residentially and commercially, the lowest you're allowed to design a building or house to cool down to is 75 degrees. Stop designing buildings for 70 and 72 degrees. If you design it for 72, you have to run it at 72, which means the place is always cold, which means people are going to put heaters under their desk, or at home they're going to sit with a blanket on the couch in the summer. 75 is the legal minimum you're allowed to design any building for, pretty much anywhere in the country. In any case, 75 was the target because it was the code number, and it ended up being 48% humidity. Everyone's happy. That same piece of equipment, if it's not fully occupied or it's not as hot outside, it's going to have to cycle the compressor or compressors on and off more. I'm still going to get my 15,000 CFM, but now my average dew point off the coil is 65. It may be 50, and then it may be 70, and then it kicks on again, and it's 50, and it's off, and it's 70, and in this case, it averaged out to 65. I'm still going to get 75 on the thermostat because that gets whatever it wants always. The thermostat's the only thing happy in every single building, but the resultant relative humidity in the space is 71%, which is a problem. Indoor air quality standards like ASHRAE standard 62, 65% is the maximum indoor humidity. Actually, on the old ASHRAE 62.1 it is. Now it's switched to a dew point number, but it's easier to express it in percent for the purpose of our discussion, so we'll pretend it's the old standard and it's 65%. ASHRAE standard 55 for human thermal comfort has a cap of 60%. Otherwise, people are going to object to their comfort level in a more humid space. In either case, this dude's over the limit. So what ends up happening is the consumer, the occupant of the building, drives the 75 number down to 73 or 72 or 70 or 68, or whatever number they have to drive it down to in order to get that humidity down into the 50% something so they're comfortable again. They end up using the thermostat temperature as a way to inadvertently set the indoor space humidity. All right, and then they complain it's cool in there, right? Yeah, it's cool because you jacked it down, but if you don't jack it down, it's humid. An ERV is going to help a lot with that. I mean, it's not going to help with you oversizing the equipment side of the equation, but it's going to help with the fact that the outside air conditions are one of the biggest challenges in the humidity control of the building. Your air handling system, and rooftops are even more challenged than like a chilled water, hot water air handler, but your air handling system, whether it's an air handler or a rooftop, has to deal with these really cold 0-degree days, has to deal with these hot 95-degree days, has to deal with humid days, has to deal with dry days, and essentially everything on the psychrometric chart in this red bubble becomes the problem of your air handling system. And it has to try to cool it, heat it, humidify it, dehumidify it, even if it even has a humidifier. If you have an ERV on there and you're going to pre-treat the outside air, right, warm it up from that -10 to 50 degrees like we just talked about with that ERV, or cool it down in the summertime and dehumidify it, you're going to pre-warm it in the winter, pre-humidify it. In the summer, you're going to pre-dehumidify it and pre-cool it. And now your air handler or rooftop only has to deal with the blue bubble and not the red bubble, which means that it's significantly easier for the capacity control in that unit and it having a chance of providing comfortable conditions in there. I don't see any questions, so I'm just going to keep on talking here. So the four major types of ERVs that we have. We'll start with the most traditional and simplest. Traditional meaning we've had these since like the 1960s, 70s, 80s kind of thing. We have a runaround loop. This is still utilized, by the way. It's not compliant with energy code for places that require an ERV, but you can use it in places that don't require an ERV, right? So it's not that it doesn't save energy, it just doesn't save any latent energy, which is a code requirement nowadays. But it's utilized currently in places that are like industrial manufacturing facilities where there is no code requirement to do this, but you're like, dude, there's a lot of heat going out that exhaust duct over there, man. There's just a ton of heat. And then over here, we're sucking a bunch of fresh air in. Like, what are we doing, man? And what you'll do is you'll put a hot water coil without the hot water. So you'll put a hydronic coil in the exhaust air. You'll put another hydronic coil in the ventilation air coming into the building. And then you'll run piping between those. It's a circulating pump like we use on a hydronic system, an expansion tank, all those normal things that we have. But what you'll notice that's not on there is there's no boiler or chiller or anything that makes heating and cooling. All it does is just moving water from this coil to that coil, back and forth. And if I have warm air leaving the building, let's say I'm exhausting 80-degree air or something like that, and I'm bringing in 10-degree air, that 80-degree air warms up the water in this coil. That water gets pumped over to the other coil, and maybe the water's, 50 or 60 degrees, and that 50 or 60-degree water pre-warms up that 10-degree air coming in. And then, yes, downstream of that, I'm going to have something else for heating and cooling and whatnot. But it's going to precondition that air with these coils. This works good in places, like I said, that are A, not requiring an ERV per the energy code, and B, where the two airstreams are far apart. If they're right next to each other, this is not my best choice. But if they're really far apart, it's much easier to run a bunch of 2-inch pipe around the building than it is to run a bunch of, 4-foot wide ductwork around the building. I'll try to get air near each other. The next type that we have would be heat pipes. So what a heat pipe is, each one of these little pipes in here is a copper pipe filled with refrigerant, but it is not attached to anything. There's no U-bends on the end of this coil making it to one big coil. Those aren't there. They're gone, right? It's just an individual pipe. Each one of these is one individual pipe all by its lonesome. And we're using the warm airstream, whether it's in heating or cooling, the warm airstream to heat up that refrigerant. And that refrigerant then migrates to the other side of the pipe, which is in the other airstream, where it can give up or collect heat, depending on which side is which, right? So let's say it's winter time. I have warm air I'm exhausting out of the system. I'm bringing cool, once again, we'll say 10-degree air in. That warm air leaving, let's say it's 80 again, just for argument's sake. He gives some of his heat to these pipes in the duct here, and then the refrigerant in those pipes, when it warms up, it migrates over to the other side. And then cold refrigerant migrates back the other way. And there's like a little mini circulating loop happening in each of those individual pipes. The vapor-based refrigerant on the top of the pipe moves along, and then the cool liquid-based refrigerant on the bottom moves along the bottom. It's like a little baby refrigeration cycle. It does not get cool enough without a compressor to be able to get down to the dew point of the air. Hence, you can do no dehumidification with it, so there's no latent recovery. So it is not something you can use for code compliance with the IECC. But if you do not need an ERV for code compliance reasons and you just want one, this could be a potential option for you. The other two types come in flavors that are code compliant and non-code compliant. And once again, non-code compliant doesn't mean you can't do it. It just means you can't do it for projects that require it for code. So one of them will be a fixed plate style heat exchanger. We've been using these residentially for a very long time. And then for, I don't even know, 2 decades or something, they're available commercially. They're just much larger. Or sometimes instead of larger, it's a bunch of these small residential sized ones banked together. I mean, granted, this one's actually a little bit bigger. Each one of these up here is like, let's say 400 CFM, and this dude down here in the bottom was like 100 CFM. But conceptually, it's a bunch of little residential ones banked together to make a giant version of this. So that heat exchanger is going to sit in the airstream, and those same 4 connections I showed you on a wheel are going to be here. Return air, leaving, so the return air comes in. Let's just do the same. I'll use the same numbers I used all along, right? Let's say it's 80-degree return air, which is kind of warm, but let's just say that. And it's 10 degrees outside. That 80-degree air goes through the heat exchanger, whether it's a little one or it's a bunch of them banked together. Either way, goes to that heat exchanger and gives up its heat to the 10-degree air coming through the other side of the heat exchanger. The air molecules don't touch each other. One is going on one side of the metal on different channels, and the other one's going on the other side of the metal in different channels. And The 80 degrees is warming up the metal plate, and the metal plate is warming up to 10-degree air, and the 10-degree air ends up being something else, let's say 50 for argument's sake, and that 80-degree air ends up being something else, let's say 62 or something like that. His heat was given up to the other airstream. If it's a metal plate, it's going to be sensible only. And that's what this is showing up here. But you can get versions of this that are not a metal plate that do have the ability to do latent. So latent ones are now readily available on the market, and by now I mean the past like 15 years. So you can get ones that do enthalpy transfer as well, where they basically can wick moisture through them in addition to the temperature warming up one side of the heat exchanger and the other. So you can use these for code compliance on projects that require them per the energy code. The wheel is the fourth type that would be of the four major common types, and that's one I was showing you earlier. The nice thing about the wheels doesn't take up as much space, right? You can imagine how big an air handler could get, and if you think about it, how much pressure you got to use from the fan system to push air through all of that heat exchange material. All right, that thing over here is like 4 feet thick, whereas this wheel is like 3 inches or 4 inches thick. So it's much easier to push airflow through there. I do have to pay to spin the wheel, which on the fixed plate I don't have to do because obviously it's called a fixed plate, so there's no spinning. So there's a little bit of energy cost there, but that's usually like an 1/8 horsepower motor spinning this wheel at like a ridiculously low, like 45 or 90 RPM type thing. So it does. The ERV wheel takes up less space than the fixed plate, and it does a better job of transferring the energy. I'm saying that, and it's not because I have some kind of hatred towards the fixed plate. Our company does a lot of fixed plate ERVs, and we do wheels as well, and we do all the types. But there's just so many more applications where I can utilize this wheel and get more benefit out of it. However, there are applications where a wheel will not be allowed, and I'll have to use the fixed plate. So there's a trade-off, and you have to be prepared to use both styles on different projects. The wheel is going to rotate slowly, like I mentioned. 45, 60, 90 RPM. So if you've never seen one before, the first time you see it and you see it going around like a little kid's carousel, you're like, what the heck? This thing's broken. And I literally thought that the first time I saw one in the 90s, I literally called the guys at the office. I'm like, dude, this thing is effing broke, man. It is barely moving. And they're like, it's supposed to be barely moving. If it goes too fast, it doesn't have any time to transfer energy, dude. It's got to go slow. I'm like, oh, okay. So it goes through the air relatively slowly, so it has time to absorb the BTUs of the air. If we go to our same example, 80-degree air coming in on a 10-degree day, right? That 80 goes in, gives its heat to the heat exchanger. That heat exchanger actually spins into the other airstream, right? And I get my warmer air out, whatever it happens to be, right? 50 degrees in this case, for example. The reason why this is not allowed in certain applications by code is, unlike a fixed plate, this can be sealed, this can be sealed, this can be sealed, this can be sealed, and the front door and the back door going on, it can be sealed. And you can pretty much guarantee there's no leakage between the two airstreams because you can seal everything up. On a wheel, you cannot seal everything up, right? You can seal the doors in the cabin, obviously, but I can't seal like this little edge right here because the wheel has to move. And if I seal it and caulk it up, it can't move anymore. Right now, it's got one of those like little door sweeper things, like the bottom of your door at home, to kind of block, some of the excess stuff. Right, so it does a pretty good job, and you can get ones that are like really low leakage, like 0.01%, which for the average person we would say that that's no leakage, that's basically zero, dude. But in certain applications, from a code perspective, that's not zero, that's 0.1, hence not zero, and you might not be able to use it. So, for example, in most places, like in suburbs, there might be like laboratory applications where you have caustic air that may not be something that would eat up an ERV wheel, so a wheel would be allowed to be used by the manufacturer of the wheel, but because you might leak 0.1% of this air back into that air, it may be a no-go. If it's bathrooms and you leak 0.1%, or even if you leak 1%, even if you leak 5% of your bathroom toilet exhaust and it doesn't go out the building and it accidentally comes back into the building, no one's going to notice. 5%. Bathrooms aren't exhausted because someone's going to die. Bathrooms are exhausted because they smell, right? But a 5% amount out of a small bathroom fan going into a large air handler, no one's going to notice. And the code actually allows you to leak up to that 5%, except the city of Chicago. City of Chicago, it's no leakage. So if you're in the burbs, you can use wheels on toilet exhaust. If you're in the city, you're going to have to use fixed plates on almost every kind of project that you do. But this is why we like to use the wheels. The wheels have the ability to recover. These are all equally, equal amounts of airflow going through them. But for the same amount of airflow, an ERV wheel can do significantly more BTU transfer. So if you can do the job with a wheel, it physically is it's code-wise allowed to be used, you should use a wheel. If you can't use a wheel because it's some kind of class of air that can't accidentally get recirculated, then you're going to move over to fixed plates. Right? And you're not going to use heat pipes or run-around coils or sensible plates unless it is a project that does not have to comply with IECC for an ERV. And you have certain reasons why these might be better for you than others. Getting this to work with your given space, there's a couple ways you can do this. You can have an ERV be a standalone. It's kind of dumb. I wouldn't do it very often. Standalone means it's got these these 4 air connections on it like we had before: return, exhaust, outside, and supply. And this supply goes directly into the space with the occupants. It doesn't go to another piece of HVAC equipment. It just brings that 50-degree air in and dumps it right into the space. So you can imagine, even though there's a system over here with an air handler heating and cooling these people in this office, if I start dumping 55-degree air on this lady's head, she's not going to be super happy. So for most spaces, you can't do it this way. I mean, you can, but for most spaces, you can't because it would be objectionable. The place this does happen seems to be if you're going to do like mini splits on the wall, right? I got this or VRF, right? Mini splits in VRF, and those guys have their piping going up to their condensing unit, doing their thing. I might have to bring the outside air in like this. If I'm going to do that, I'm probably going to want to get an ERV that has heating and cooling in it as well, not just an ERV, right? And then in that case, it is no longer a standalone ERV. It is now called a dedicated outside air unit because I'll have to have heating and cooling in there to temper that back up to a more neutral 70, 75, or whatever it's going to be. You could have also, in this exact project, not bought a dedicated outside air unit, bought just a plain old ERV, and then instead of ducting it into the space, duct it into the return of the air handlers. So here's the return, and that's where the outside air was expected to come in. Just go ahead and duct the ERV right into there. Right? So instead of an outside air duct going outside, it just happens to be an ERV. So as far as the air handler is concerned, he's mixing return and outside air like normal. The outside air just happens to be much warmer or much cooler or much more dehumidified than normal. It no longer thinks it's in Chicago. It thinks the project's in San Diego. So the coil doesn't have to be as big and all of that. And this works well for a lot of projects. We're obviously showing 2 air handlers here, but it could be a bunch of little fan coils. You could have, 36 different little fan coils all being fed off of one ERV if they're going to have similar, occupancy schedules and stuff. You could also take the ERV, all the technology, wheel, fixed plate, whatever it is, and stick that whole thing into the air handler. When you do that, you're going to end up with a stacked air handler. And the reason being is I have to have the ERV. In this case, it's a wheel. I can tell because the return and exhaust are both on top. If it was a plate, then these 2 guys would have to swap each other. But I got one airstream going through this way, one going through that way, and then in this case, there's a wheel ERV in between them doing the heat exchange process. So you need a little more height in the mechanical room to do this, but you can put a wheel inside there. When you have an ERV, whether it's an air handler or a rooftop or any other type, the code is also going to require you to put bypass dampers in to go around the ERV. The reason being is the ERV wheel is stupid. It's a heat exchange media. It doesn't know anything about what it's doing. It just takes the hot thing and transfers it to the cooled thing. Heat always goes from hot to cold, and it's just following those laws of physics, right? And transferring the moist thing to the dry thing. So what that means is when you have an economizer day, meaning it's cool outside and your building wants cooling, and you would normally open up your economizer damper, if you have an ERV, it's trying to recover the energy out of your exhaust air and use it to preheat your free cooling air coming in. But you don't want free preheat. You want cooling. So you don't want to have an ERV running on an economizer day. You have to shut the ERV off during an economizer day. So when I do that, just stopping the spinning of this wheel is not going to be awesome because I still have to push air through there from a fan pressure drop standpoint. So the code requires you to open up a bypass damper on the 2 airstreams. And don't ask me why on this particular picture one's closed and one's open, because that would never happen. That's stupid. But that's the way that this picture was taken. So obviously this one's not even started up or anything yet. But Sometimes too, the ERV will be much larger. It'll take up the whole cabinet. So this is a tall, skinny one, but it could be a much larger, wider air handler. And in that case, sometimes up in the four corners around the wheel, there'll be the dampers. And you might do it that way as well. So in general, what's happening is the return air is going through. It's getting filtered. That's not normal for regular air handlers. There's an extra filter in here that you don't normally have. Instead of just the one main filter for the air coming through the heating and cooling coil, you also have a filter on your exhaust air leaving the building, which sounds so weird because it's exhaust air leaving the building, but you have this because you don't want any crap on the heat exchanger. You don't care about dust leaving the building. You just don't want dust on the heat exchanger. So you have a filter set there, goes through the ERV. In this case, it's a wheel, so it's spinning, right? And then it exhausts out the building. The outside air comes in, gets filtered on that side of the equation, goes through the ERV and picks up the free heating or cooling or dehumidification energy or humidification energy. And then if needed, it cools it or heats it more, and then it goes out to the space. So hopefully that makes sense. Don't see any questions, so we'll hit the last couple things on here. There are some other really cool things you can do with this technology, whether it's the wheels or the plates. And this one's showing a plate example. You can do the exact same thing with a wheel. This right here is the ERV we've been talking about all along, but you can put a second ERV in the air handler and do some other cool things. So in this case, outside air is coming in, return air is leaving. It's giving up its extra heat to this heat exchanger core, and I'm using that to preheat the air coming in, or if it's summertime, pre-cool the air coming in. And then what ends up happening is that air then travels through another ERV where it gives up whatever heat it has, goes through a cooling coil to be cooled down below the dew point and hence wring a lot of moisture out of it, and then it wraps around itself and goes back and picks up the heat that it just gave up. I know that sounds kind of weird, right? It gave its heat to this core, got cooled even more, down to the dew point, drained it out, and then picked up the free heat. The reason why we do that is you are no longer allowed to subcool air and then reheat it. That is not permitted by code. So to dehumidify a space, you can't drive down the air handler's evaporator coil to a really cold operating point and then throw an electric heater or hot water coil in the duct and reheat it back up. That's not allowed by energy code. It's wasteful to cool air and then heat it again. But you are allowed to use reclaimed energy to reheat air in that mode. And there's different ways to get reclaimed energy, and this is one of those ways. We pulled the energy out of this air, dropped it down to the dew point, and then reused that old energy, that reclaimed energy, to heat and temper the air back up. So there are some unique things you can do in that regard. You can also add ERVs, add a wheel to the existing duct system of an air handler. This is not very common at all for two reasons. One, it requires everything to kind of be lined up perfectly where all the ductwork's near each other, like literally right next to each other. And then two, when we put an ERV in, like we said, it reduces the heating and cooling capacity that we need for the system, and you should be putting in a smaller rooftop or a smaller hot water coil, a smaller boiler, a smaller everything. So by doing this as a retrofit, you're basically adding this to equipment that the equipment gets grossly oversized at that point. So unless you were changing the usage of the space and needed more capacity anyway, you probably wouldn't retrofit this, but you could do it. You can build it into the air handler, like we said before. In this case, it's an outdoor air handler that does heating, cooling, and energy recovery. We call that a dedicated outside air unit. You could do it that way. You could do like I was talking about at the beginning with the cost-effective scenario, where I take a standard packaged rooftop unit, and on the roof I duct it together and interconnect it with an ERV. Right, that allows me to have a low-cost rooftop unit, and as opposed to something like this, which is more, I'm not gonna say custom, but it's more specialized, so it does cost more than a regular rooftop where they're making 10,000s of them. You can duct them together on top of the roof. You can duct them together below the roof line. Right, so in this case, the return air from the space, instead of going to the rooftop unit, this damper could shut off, and that return air can go out the ERV be sitting right here in this case, out the ERV, give up its energy to the heat exchanger, etc., and then the fresh air coming in could go take its place. And the rooftop doesn't even know this thing is over here. It's doing its own thing. It just happens to get air that's better conditioned than it thought it was going to get. You could also get what's called a combo curb, where this curb and this curb are physically one curb, and this ducting right here is physically inside the curb. So we've done that a lot over the years. We don't do it as much anymore because there are dedicated outside air handlers, but those didn't exist 20 years ago, at least not in large options and quantities. So we did this a lot. We would take a rooftop unit and ERV, put them on what we call a combo curb, and inside that curb, all that ducting was built to exchange between them. It looked like this. It's kind of an ugly curb, but it's on a roof, so no one sees it, so who cares if it's ugly. But inside there's 2 duct airflow streams. You can also get ones with regular rooftop units with an ERV on them. Basically, it's an appendage that hangs off the side of the unit exactly where the economizer and the power exhaust would have hung. Instead, it's a ERV. An ERV is an economizer and a power exhaust. It just happens to have a heat exchanger, a wheel in this case, between those 2 airstreams. So get the air close to each other, and then you have an ability to recover energy from the exhaust air to the outside air. Think about what type of technology you want to use. If possible, use wheels because they're going to save you significantly more energy for a given amount of space and CFM. I mean, a 30,000 CFM ERV with a wheel takes about as much space as a 12,000 CFM with fixed cores. So you can get more done in a smaller cabinet. But sometimes you can't do it because it's not allowed, and so be it. And then whether you're working with my company or another company, preferably my company, although I'm not involved in sales, so I don't care. I mean, I care, but I don't care as much as the sales guys. They should be using some type of software to give you the data. This happens to be the software we use. I did this one a long time ago, but I keep using the same example because I like it, and I'm also lazy. So this was a 95-degree -10 winter condition scenario, and on that day, on a 95-degree day, coming off of the ERV, this was a wheel in this case, we had 80 dry bulb, 67 wet bulb. That's not by accident. I specifically selected that one for that point on purpose. That's a pretty good target point because it's like the evaporator doesn't know you have outside air. And then on a -10-degree day, it was 51 degrees coming in. Oops, I just kind of slopped that over there. But 51 degrees coming in. What that meant was they needed to get a rooftop unit that was 3.8 tons smaller and 120,000 BTUs of heating smaller, right? And this particular software, you could do that for this air handler and all the other air handlers, and then it will actually add them up and give you the economics. So this was 11 ERVs on this fitness center. They ended up not getting, I think, this one and one other one and this one. The ones that had the small amount of energy savings are like, not worth it. And they just did the bigger ones, which is fine. So they did 9 out of the 11. But what it does is it tells you all the airflows and the BTUs of cooling saved, the heating BTUs saved, the dollars of cooling, depending on your utility rate at the time this was done, which back at the time this was done, it was 10 cents electric. Now we're more like 16. And it was $1 a therm, which is actually not too bad. We're probably like $1.10 right now with all fees included. But it tells you the cooling savings and the heating savings in terms of dollars. It tells you the fan energy waste because it takes more fan energy to push air through an extra heat exchanger. And it adds the heating and cooling and subtracts the fan and gives you the net result. So in this case, the cooling was only going to save $3,500 and it was going to cost $4,600 for the fan energy. So for cooling, you're not necessarily doing this for pure energy savings. You might be doing it just because you want that awesome extra dehumidification. But look at the heating side of the equation. Save $32,000. In total, $31,000 in savings between the heating, cooling, and fan penalty. And then what I normally do is I take stuff like this, whether it's an ERV or a cooling tower or a boiler or whatever it is, and I put it in a spreadsheet like this. And I'm happy to send this spreadsheet to anyone who wants it, as long as you don't work for my competitor. No, I'm just kidding. I'll send it to you, but I'll change some of the math formula so it calculates wrong. No, I'm just kidding again. But I take this sheet like this, and the stuff in red I delete before I send it to anyone. It's just my notes, so I remember what some of these terms mean. And the reason I made this sheet was because I didn't know what any of these freaking terms meant. People would ask me on stuff like, yeah, great, Ryan, it's going to save $31,000. Yeah, but like, what's the payback? Okay, I can calculate a simple payback, 2 years in this particular example. But like, well, what's the net present value? And I'm like, I don't know what that means. What's the internal rate of return? Like, the heck would I know? So I literally sat down with one of the guys in our office that was working on his MBA, and then one of our accounting guys. I'm like, you got to explain this stuff to me. And like, we need to do it. And they're like, oh, we use this spreadsheet. I'm like, dang it, where was that at? Why can't we use it for HVAC? So in any case, I punch in the ERV cost, $54,000 in here. The extra cost for the extra curbs, $23,000. The rooftop curbs that I'm not going to buy. I'm going to buy combo curbs, so I'm not going to buy rooftop curbs, so I get a credit for that on the project cost. I only care about how much more it costs than doing the job without it. I don't want to know how much the whole job costs. I want to know how much it costs to upgrade the job to add ERVs. Or if this is a boiler project, how much does it cost to not replace the boilers with crappy 84% efficient boilers and instead replace them with 94% efficient boilers? What's my difference in cost, right? So some of these things are extra cost penalties, and a couple of them were cost credits. Extra labor involved, a little bit extra maintenance because you got more filters to change than you otherwise would have had. What I guessed inflation would be, that's a crapshoot, right? What I guess energy costs to increase for, that's also a crapshoot. Customers discount rate, they give you that. And then it gives me a cash flow statement. And after 2.1 years, I'm ending up being positive cash flow. And after the course of 15 years, and I use 15 years because that's pretty much the average life expectancy for any HVAC equipment mounted in a sheet metal box outside. It's going to generate $590,000 in cash flow for them. But if I take that back to today's dollars, back the inflation and stuff out of it, it's $400,000, $403,000. That's the net present value, $403,000. That means if they do this project, it's like someone handed them $400,000. They have to wait 15 years to get it in small pieces over those years, but it is literally worth $400,000. And that kind of corresponded to a 51% rate of return on their investment. So if they have a really good stock tip that's going to get them more than 50% return on their investment, they should buy that thing and not buy this thing. But if it's going to be less than 50%, they should spend their money on the ERV, the boiler, the cooling tower, the steam traps, the whatever it happens to be. In summary, free money from North Shore Gas and Peoples Gas. If you do an ERV, 75 cents per CFM, you just multiply it out. It's CFM input, so that's outdoor air CFM in this case. You might have 1,000 CFM of outdoor air coming in, but you may only have 900 CFM of exhaust going out because they want the building slightly positive. And they're like, well, which one do I use? You use the input, the air coming into the building, the 1,000 CFM of outside air in this case. And then for ComEd, which usually overlaps well with North Shore and Peoples for the electric side of the equation, you can get an additional 20 or 10 cents per CFM depending on the kind of ERV you're going to use. And that one is based on supply CFM, which is the same as the outside CFM. The outside comes through and it becomes the supply air when it leaves the ERV. So it's the same CFM number that we used on the gas calculation. These are people that I blatantly ripped off their photos from. Some of them are companies I work with. Some of them are competitors. I don't care that I stole from them because I'm not a nice person. No, I am a nice person. That's why I give them credit, even though I don't represent them. Any other questions come up? That's my email if you want to hunt me down later and be like, hey, you said some weird thing and I want to know what the heck that meant. This is a 45-minute version of what is normally like a 2-hour class. So I skipped a bunch of stuff just to kind of get it in. And I still went 2 minutes over. Dang it, Glenn. I'm so close.
That's okay. That's okay. I don't see any questions right now. Let me change it over to me.
And I think we recorded it as well. So
yeah, it's recorded, so it'll be put on the
our coworker. That'll be an option as well.
Yeah, it'll be put on the website also. So please visit tradeallycenter.com. And there's my information also. If you need to go to Ryan, you saw his information at TEC. If you need any help with anything, please get a hold of me. If you need help contacting Ryan, get a hold of me. I text him on a regular basis and talk to him. So thanks again, Ryan. It was a great job. I hope to see everybody next month when Tony Rinaldo is presenting on the blowdown.
Sweet. I love Tony, so everybody should jump on.
Yeah. Thanks again, Ryan. Thanks again, everybody, for attending, and we'll see you next month.
All right, cool. Thanks, Glenn. Thanks, guys.